Okay, so we're talking about the mole, and we started with cereal day and talking about the bowl. And part of the problem with the mole is that there's not a lot of words that mean a number. And that's why everyone always tells you it's like a dozen. But if you had something called a bowl, and that bowl was supposed to be 175 pieces, and it could be cereal or it could be chicken or whatever. So you can see from these images that 175 pieces, they don't necessarily look the same. They don't have the same properties. All they have that's the same is the number. And while each of these may not have the same mass, they do have the same number of cereal pieces. And we would call that a bowl, and it would be 175 in each case. So if I asked you how many things would there be in two bowls, then that means you would have twice as many pieces, which would be 350. And hopefully that makes some sense. Um, and that the mass would be different, right? So if the bowl of Cheerios weighs 30 grams, then four bowls would have four times that 30 grams. And basically, what this is doing is giving you a chunk of something that's a small item so that you don't have to talk about the individual thing. You're talking about more of a serving size. And other words that mean numbers besides a dozen, which is what everyone told me. You could say, "Give me a case." It could be 24 bottles or 24 cans, or you could say a gross of something is 144. If you say a ream of paper, that would be 500. So a mole is just a word that means 6.02 times 10 to the 23rd. And the reason we need such a large number for atoms is because atoms are so small, they can't be seen with a microscope. That it takes that many before you can really start weighing out what a mole is and start seeing these elements for gram quantities. And the other great thing about it is all these mass numbers, which were based on protons and neutrons, all were converted to grams. So if you have 6.02 times 10 to the 23rd atoms, then all of these would turn AMU into grams, and that's very helpful for what we're doing in the lab. So gram quantities you can measure in a lab, and that requires having 1 mole of any one of these substances. So it was a Amadeus Samagadro. I don't remember if I'm saying his name right, but anyway, that guy. um, Avogadro, yeah, Amadeus Avogadro, who sort of stumbled upon this number when he was doing all his calculations and realized that it had to be significant and that it turned everything on the periodic table to grams, which was very helpful. So, how much is 6.02 times 10 to the 23rd? Well, if you consider how small a cell is, and a cell has lots and lots and lots of atoms in it, which maybe you'll appreciate a little later in the year. But if a cell, which is very small, microscopic, and if each body has 60 trillion cells, and there's 7.8 billion people on Earth, you still wouldn't have a mole's worth of cells on Earth that are human. There'd only be about 3/4 of a mole of human cells on Earth if you counted all the cells of all the people on Earth. So it's a really big number, and the more we talk about that to give you an appreciation for how small an atom is. So basically, one atom of carbon, if you go to the periodic table, right? So one atom of carbon weighs 12 AMU, right? If you had one atom, it would have 6 protons and 6 neutrons, and that would be 12 AMU. But if you have a mole of carbon, then you have 6.02 times 10 to the 23rd atoms. And if you have a mole of carbon, now you have 12.01 grams, which is helpful. Oops, I guess I don't need G twice since I got grams written. All right. So one atom of sulfur, going again back to the periodic table, sulfur, one atom would weigh about 32 AMU. It would have 16 protons and 16 neutrons. So it would be 16 AMU. Whoops, 32. That's how long it takes me to forget something. Um, 32 AMU. it would have the same amount, the 6.02 times 10 to the 23rd atoms. So just like with the cereal, these have the same number of atoms, but the mass of carbon is significantly less than the mass of sulfur. And 1 mole of sulfur would then weigh 32 point, what was it, oh 01? 32.06. 32.06 grams. Again, that comes from the periodic table. All right, so let's do some math, right? So we did the horse racing, and the whole point of the horse racing was that if you bet 1 mole on any of these atoms, then what you would get back is the mass. You would get the mass back. So if you bet 1 mole on nickel, you would get 58.7 grams back. And if you bet 1 mole on fluorine, you get 19 grams back, right? So it's different amounts depending on which one you're going with. And the same thing is true with that was sort of the point. The point was A, that grams gets larger. You get a larger number of grams than you do moles. And B, that each one is different. So if we were going to look at tin, tin is number 50. So you're looking at 118.71 grams per 1 mole. And if you look at barium, barium's over here, and you're looking at 137.33 grams per 1 mole. Then here's sort of that goofiness that we do. Oxygen is diatomic. So now oxygen is O2, not just O. So even when you go look here and it tells you it's 16, right? Hopefully I'm still red for Dr. Hart, my advisor at Ohio State. So 16. So you want to say it's 16 grams, but it's times 2 because there's 2 oxygens. So that would be 32 grams in 1 mole. When we say the word oxygen, obviously you can have oxygen exist as one thing. Water has only one oxygen in it, right? H2O has just the one oxygen. So it's not that oxygen always has to be paired. It's just when you say oxygen, like you say barium or tin or gold, it is paired in that case. And that's a little mind blowing and it's a little silly, but it's the diatomics. So the diatomics are Brinkelhoff, bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, fluorine. It's seven. 1, 2, 3, 4, 5, 6, 7. Those 7 elements that make a number 7 on the periodic table, and then hydrogen's over there. All right. Well, that's some jibber jabber. Hopefully that made some sense to you. All right. Let's do some math. So if we're talking about silver and we have 2.50 moles and we need to know how many grams that is, then we want to put moles at the bottom and we want to put grams on the top. And moles to grams, the thing to think about here, the units of the periodic table are grams in 1 mole, right? So all of these things were 1 mole. Everything's in 1 mole. So grams in 1 mole of silver, that's 107.87 grams in 1 mole. So 107.87 grams, and that is in 1 mole. So you multiply 2.5 by 107.87, and 2.5 times 107.87, and you get 269.675. All right, so that should be red, my bad. But the moles cancel and you got grams and you get 269.67. So we would like an answer with significant figures. If we're going to count all that, this has 3 significant figures. So you want something with 3. So 270 with a decimal point would give you 3. Probably don't worry about that. All right, how many moles in tin and 1547 grams of tin? So we have, we're starting with the red now, 1547 grams. Oops. Oops. 15. 15.47 grams. And we got to go from grams to moles. So now what we get off the periodic table is going to go on the bottom. And since the periodic table is always 1 mole, we'll put 1 mole on the top. So let's go check out the Tin Man again. So the tin is here. It's 118.71 grams in 1 mole. So we're going to divide 1547 by 118.71. And we're going to get 13.03. which is grams, and that's 4 significant digits, so that works. All right. So hopefully that all makes sense. Then the craziness happens with the number of atoms. So this is not fun. Anytime you have a number of atoms, and again, number of atoms is going to be a big number because it takes a lot of atoms before you can even see them. So 4.70 times 10 to the 24th. When you see that word atoms, that means you need your 6.02 times 10 to the 23rd. And the way you're going to cancel atoms is using 6.02 times 10 to the 23rd atoms are 1 mole of anything. So that's true of any substance. Would I go with purple? 1 mole. All right. So we're going to divide a big number by another big number. And as we saw in the little video about how to do this on your calculator, which I can't show here, but you got to make sure you put your denominator in parentheses if you're not using E. So if you're not using 4.70 E24 divided by 6.02 E23, that'll work out fine. You'll get a fine answer, which is what I'm working on here. Hold on a second. Let me tell you what that answer is. The answer you get is 7.81 moles, which is our answer. All right. But if you don't like the E, if you're going to do 4.7 times 10 to the 24 divided by, you need to put the 6.02 times 10 to the 23 all in parentheses, or else it'll just divide by the 6.02 and then bring the times 23rd up to the numerator, and you'll get like a times 10 to the 49th or something. So make sure that's how you're doing that on your calculator. Anyway, so your answer is 7.81. All right, atoms to moles. So doing it the other way, we're going to want a large number. So we're starting with the 4.56 moles of helium. And we got to go from moles to atoms. So we're going to need Avogadro's number on top to make that number really big. And then we're going to want 1 mole on the bottom to cancel the moles. And so 4.56 times 6.02 times 10 to the 23rd gives me 2.75 times 10 to the 24th. Oops, I want this to be this color. 2.75 times 10 to the 24th atoms is how many atoms of helium you would have. All right, so basically grams to moles, moles to grams. Again, there's another video about this where I sing the song about the periodic tables where grams turns to moles, right? And it's always 1 mole. It's always 1 mole. And then 1 mole also equals 6.02 times 10 to the 23rd atoms. It'll also equal some other things we'll talk about tomorrow, formula units, molecules. But anyway, when you're talking little itty bitty things for a mole, then you need that big number. So if we had to go from atoms all the way to grams, do you see how this is a 2-step process? 1, you convert to moles, and 2, you convert to grams. And if we have to go grams all the way to atoms, it's a 2-step process. 1, you got to turn grams into moles, and then you turn moles into atoms. So here's an example of that. If we have an iron person who has this many atoms, there's that word atoms, so you know you need 10 to the 22nd atoms. So you know you need Avogadro's number, and because that's a huge number, we want it on the bottom. 6.02 times 10 to the 23rd atoms. And that's how many atoms there are in 1 mole. So that gets rid of atoms, but it's asking for grams, and grams is not moles. So we got to go again, this time to the periodic table, and see the mass of iron. And the mass of iron is 55.845. We want to use that up on top here, 55.845 grams. Moles cancels, atoms cancels, grams is there. So you want to multiply 9.25 times 10 to the 22nd times the 55.845 grams, and then divide that number by 6.02 times 10 to the 23rd, And again, if you're using the caret, you're going to want to put that in parentheses. If you're not using the caret, if you're using E, you should be okay. But this works out to be 8.58 grams. So look at that. So that's not so bad, right? Look at all those atoms, and it only weighs a little bit. All right. Then going the other way, if you start with grams, so in this case, we started with atoms and we went all the way to grams. So now we're going to start with grams and we're going to go all the way to atoms. So we're going to do everything we just did, only backwards. We're starting with 56 grams of neon, and neon has a mass of 20.18 per mole. So we want those 20.18 grams on the bottom, and we want the 1 mole on top. So while that takes care of our grams, it does not take care of our moles because we want to go all the way to atoms, and atoms means we're going to need Avogadro's number. So we want Avogadro's number on top this time because we want a huge number when we're done because it's atoms. And then we want 1 mole, oops, wrong color, 1 mole on the bottom to cancel there. So 56 times 1, whoops, 56 times 6.02, 10 to the 23rd. And then we're going to divide that by 20.18. And you get 1.67 times 10 to the 24th. So that is 67 times 10 to the 24th atoms. Whoops. Thank you. All right. So there's lecture 1.